let us now take a look at some of the important properties of the Laplace transforms. We use the notation that f of t has the Laplace transform f of s, and f of t is the inverse Laplace transform of f of s, capital F of s. Most of the properties that we are going to discuss parallel those which we had already discussed in the context of the Fourier transform. So, as we go along, you compare the properties that we are discussing here with those that we had discussed earlier in the context of Fourier transform. They more or less are similar, except for minor variations which arise as a result of the fact that the Laplace transform concerns itself essentially with causal time functions, whereas the Fourier transform deals with functions which can exist from t equals minus infinity to t equals plus infinity. So, basically that is the difference, and that creates some differences. Otherwise, the properties are quite similar. First property is something which we already assumed is the linearity property. What we mean is, if f1 of t has the Laplace transform f1 of s, if f1 of t has the Laplace transform f1 s and f2t has the Laplace transform capital F2 of s, then a combination of C1 f1 of t and C2 f2 of t, where C1 and C2 are arbitrary constants, a linear combination of these two is having Laplace transform C1 of f1 of s plus C2 of f2 of s. There is nothing much to prove about this. You plug this, find out the Laplace transform of this, you plug this into the expression for the Laplace transform defining integral, break it up into two parts, and you can easily show it. There is no difficulty in doing this. As a matter of fact, we have assumed this relationship. If you recall, when we are trying to find out the Laplace transform of cos omega naught t, we said cos omega naught t is 1/2 of e to the power of j omega naught t plus e to the power of minus j omega naught t, and therefore there we have already made use of this linearity property. So, we need not discuss this any further. This is quite obvious and it can be readily demonstrated. The second property we are going to talk about is differentiation in time domain. We ask the question, what is the Laplace transform of df by dt? This is the question which we would like to answer. Given that f of t has the Laplace transform capital F of s, we would like to find out what is the Laplace transform of df by dt, assuming that the Laplace transform of this differentiated function exists. Then we set up the differential equation, just defining integral 0 minus to infinity of df by dt e to the power of minus st dt would be the Laplace transform of this derivative of this function of time. Now, this can be integrated by parts, You take the integral of df by dt, which is f of t e to the power of minus st evaluated between the limits 0 minus to infinity, minus integral from 0 to infinity of f of t, and take the derivative of e to the power of minus st with reference to time. So, minus s e to the power of minus st dt. So, when you substitute these two limits in the first expression, in the region of convergence as t goes to infinity, limit as t goes to infinity of f of t e to the power of minus st, that goes to 0. That is the definition of the value of s that we are going to take in the region of convergence. So, at the upper limit this is 0, at the lower limit e to the power of minus st becomes 1 and therefore you have got f of 0 minus because it is a lower limit, minus of f of 0 minus. And here the integration is with reference to s, therefore s times 0 minus to infinity of f of t e to the power of minus st dt. This integral yields capital F of s, the Laplace transform of f of t itself. Therefore, this is s times f of s. So, this you have s times f of s minus f0 minus. That is the Laplace transform of f prime t, which is the derivative of f of t. This is assuming that f of t that we are talking about, we want to take the behavior of f of t for t greater than or equal to 0 minus. That means, when we are taking the derivative of the function of time, we take into account the variation of f of t from 0 minus onwards. Often we would like to find out the Laplace transform of f prime t for t greater than or equal to 0 plus. That means, any jump that this function has got in transiting from 0 minus to 0 plus, we would like to exclude. That the derivative we want to take only from 0 plus onwards, we would like to disregard whatever is happening before that. In such case, this will be the Laplace transform of that will be sfs minus f0 plus. That means, we are now talking about the Laplace transformation of the derivative starting from 0 plus instead of 0 minus. The meanings of this will become clear as we take an example. So, in the literature you find that Laplace transform of f prime t is written either in this manner or in this manner. Both are equal, both are correct, depends upon whether you want to consider the derivative starting from 0 minus or 0 plus. Let me illustrate what we mean by this by an example. Let us take f of t to be a unit step function ut. So, you have this is f of t. Now, let me say that I want to find out the derivative f prime t for t greater than or equal to 0 minus. So, I would like to take the derivative of this function starting from 0 minus. So, as you take into account the variation of f of t starting from 0 minus, from 0 minus to 0 plus it goes through a jump of 1, 0 minus to 0 plus. So, the derivative of this function at t equals 0 is an impulse, because it is jumping from 0 to 1. So, derivative is infinite, and when you integrate with the impulse you get a rise a step of 1. Therefore, the derivative describing the behavior of this function from 0 minus to 0 plus is an impulse. And from t equals 0 plus onwards there is no derivative, it is 0 because it is a flat function of time, therefore, this is 0. So, f prime of t greater than, taking into account our the variation from t equals 0 minus is a delta function delta t. On the other hand, if you want to consider the derivative only starting from t equals 0 plus onwards, from 0 plus onwards the variation of this function there is no variation, therefore, it is 0, and from all negative values of time we assume the function to have 0 value, therefore, f prime t is identically 0. So, for this that is the function. Now, let us see the Laplace transform of this we know is 1 over s. The Laplace transform of the unit step function is 1 over s. What is the Laplace transform of this? If you ask this question, f prime of t greater than or equal to 0 minus, you must use this formula s f of s. You must use this formula s f of s minus f0 minus. This is the formula that we have to be used. We want to take the derivative starting from t equals 0 minus. Therefore, you write s times 1 over s minus, what is the 0 minus value of this f of t? It is 0. Therefore, this is equal to 1, and we know that the Laplace transform of a unit impulse function which is the derivative of this is equal to 1. On the other hand, if you want to consider the derivative to be 1 which has a value from t equals 0 plus onwards, then we use this formula which is s f of s minus f 0 plus. So, that will be s times the Laplace transform of f of t 1 over s minus f 0 plus. The f 0 plus of this unit step function is equal to 1. Therefore, you substitute 1 here and that will be 0, and that is as it should be because our f prime t in this case is identically 0, its Laplace transform as well will be identically 0. So, that is the distinction between these two formulas. Depending upon how you want to take the derivative, whether you want to consider the derivative from t equals 0 minus or 0 plus. So, you can use either of these, and that the difference between these two will be the Laplace transform of an impulse if there is any existing at the origin. Now, let us now proceed further and consider the second derivative of this. That means, what is the Laplace transform of d squared f dt squared? Now, the second derivative d squared f dt squared is after all the derivative of d by dt of df by dt. Since we know the Laplace transform of this, we have to apply that formula which we already derived. So, this will be s times the Laplace transform of df by dt is s f of s minus f 0 minus, I will continue writing 0 minus because that is more general, minus the value of the derivative df by dt at t equals 0 minus. So, I will write this f prime 0 minus. So, that will be s squared f of s minus s f 0 minus f prime 0 minus. So, the Laplace transform of the second derivative of a time function in terms of the Laplace transform of the original time function is given in this manner, and this can be continued. So, a general formula for the Laplace transform of the nth derivative dn f dtn can be written as s to the power of n f of s, we are talking about the nth derivative of a time function, minus s n minus 1 f 0 minus, like that you take. Next term will be minus s n minus 2 f prime 0 minus down the line to f n minus 1th derivative evaluated at 0 minus. That is how it will be. We do not have to remember this formula. All we should know is the formula for the derivative, and then one can extrapolate this in this fashion. That will be, in fact, you can easily get this by repeating the application of the derivative formula.